Hello and welcome to the course on power electronics. Today we are going to cover the topic which is termed as Thyristor and also known as silicon controlled rectifier. I, Akbar Ahmed, welcome you in this course. Thyristor or silicon controlled rectifier is a semi-controllable switch. It can be turned on by providing a positive gate pulse across the gate terminal. It is an uncontrollable turn off feature. That means once it goes on into the on state, it requires an external commutation circuit to bring it off into the off state. We will see and cover the triggering circuits in the later stage of the video. It conducts during the positive on state current and it blocks the positive and negative off state voltage. So here we can see two characteristics. One is the ideal characteristic, which is highlighted by this yellow color, which shows that during on state, it has two basically features where you can see in forward conduction mode and forward blocking mode. And then it is provided in the negative half, it is providing a reverse blocking mode. On the left hand side, you can see this is the practical characteristics. How does it look like? And we can see here one more characteristics. This is the device rating, and as in the earlier lecture we have already seen, SCR is generally used for high power application. So in this curve we can easily observe here SCR with the MVA rating for voltage more than around 12,000 volts and 1500 ampere. It's made by Mitsubishi, whereas 7500 volts and 1650 amperes it's available in UPEC maker. Then we have ABB, which manufactures around 6000 volts and 4200 amperes, and also Westcode, which is producing 4800 volts and 5000 amperes. Now with this we can compare its family device, which is GTO, and here we can observe with the black line GTO with the similar makes. It is not able to carry the voltage as compared to SCR, but we can see here the MVA rating as compared to SCR is much higher. So similarly we can observe for the different make for IGBTs. But in this case here we can see SCRs, it's very well useful in the range of 27 MVA rating, and it's useful in the industry, that's why. We can see here thyristors indicate to a family of semiconductor devices which are used for providing a power control. We can see the symbol and observe here that it is a three-terminal device where one is represented by anode, another one here it can be represented as cathode, and the control feature is provided by the gate. Since we have already termed it as a semi-controlled device, so thyristor is also termed as a four-layer uh, and three-junction device. Semiconductor in the form of PN-PN structure with three PN junctions uh, is shown here adjacent in this figure. The word thyristor is basically coined from thyrotron and transistor, and it was invented in the year 1957 at Bell Labs, and different types of thyristors are available in market with this family of SCR, TRIAC, DIAC and GTO, and we will cover one by one each one of these. In the bottom side here we can see some of the characteristics and some of the visuality of the SCRs. So some of them looks like in a planar type construction, while some looks like in Mesa type construction. Here we can see it's in a form of nut and bolt kind of a feature. And then here we can see another one which is displayed as external construction, where the cathode, gate and anode, all the three terminals here, it's visible. Now let's see the cutaway view and the impurity profile with width of layer view of a thyristor. And it is interesting to see here that in a box where we can cut it in four different layers of Pn, P2 and N2 here, with this black metal layers, we can connect it one of the terminal here as gate, whereas the other terminal can be connected here as cathode, where N2 are connected together, and then this black terminal on the above is represented as anode. The width of each layer is not equal. As we can see here, the width is represented for P1 as 30 to 50 micrometers and N1 from the range of 50 to 100 micrometers, P2 in the range of 30 to 100 micrometers, and N2, the smallest layer, it's of 10 micrometers. Now let's see another interesting view here, where it represents the profile of impurity, which is in atoms per cubic centimeter. And here we can see in P1 layer, we have 10 to the power 19 atoms per cubic centimeter. And then in N1 region, it is 10 to the power 14. And similarly, we can say here the purest region where the impurities are least doped is N1, and P1 and N2 is similarly highest doped with 10 to the power 19, whereas P2 is at 10 to the power 17 atoms per cubic centimeter. Now let's move ahead to observe the static characteristics of SCR, which is also termed as IV characteristics. So the axis here is defined as voltage between anode and cathode, and another y-axis is represented as current available at anode. This region here on the positive half we have already seen, it is termed as forward blocking mode, and during this mode the device is not in conduction. So what happens here after this forward blocking mode, once we increase the gate current and starts providing the gate current, this is the point where the gate current is actually 0, and as soon as we start increasing the gate current, the device moves into the conduction mode. And this mode here, once the device reaches to the conduction mode, this is called as forward conduction mode. Whereas in the negative half, as we have already seen, it blocks the voltage, and that is why this region is termed as reverse blocking mode. So ideally these devices should block infinite amount of voltage in the reverse direction, which is practically not possible. So uh, then we can see some of the circuits here, how this electrical circuit is making to operate the device in forward blocking mode. So in forward blocking mode, we can observe here the polarity of positive terminal of V is connected across the anode and negative is connected across the cathode. And here we can see the gate is not provided with any current. So during this mode, the device is blocking the forward potential of voltage. Then next we can see in the reverse blocking mode here, the polarity is reversed here, and now the negative terminal is connected to the anode and the positive terminal here it is connected to cathode. So during this mode also the device is not conducting. Whereas if we see the forward conduction mode here, we can see the switch is now closed and the gate is given the gate current and the device has moved to the conduction mode. So as we have already seen, once the device goes into the conduction mode, it is difficult to bring it back into the uh, reverse, means off state. We need an external circuitry for that. Now interesting thing to see here is the ideal characteristics. It looks like somewhat this, and the 2 points here is required to be memorized. One is termed as holding current, and holding current of SCR or thyristor is that minimum value of current below which anode current must fall to come down to off state. And this means that if the value of holding current is low and the device wants to go into the on state, it should cross the value of latching current. And here we can see the latching current is defined as the current of forward biased SCR is the minimum current which anode current must attain to continue to remain in forward conduction mode even when the gate current is removed. So these 2 points are important here, and the relation between these 2 points we can observe always that latching current is almost 2 to 3 times higher than the holding current for practical SCRs. Now let us see the application of thyristor in a normal electrical circuit where the power is required to be transferred from the source to load with the help of thyristor. So let's see some of the interesting waveforms. The voltage which is coming from the input as VST is represented as a sinusoid here, and then let's see if we provide a gate pulse at certain duration here which is marked as gate pulses. So now what will be the output voltage? Interestingly, if we will see during this part with the arrows here which is represented as the gate pulses, at this point if we can see the thyristor is getting turned on, the waveform during this is clipped and it's looking like this in the red color. And during the negative half, as we can see, the device is already in off state. So this is not going to conduct during the negative half, and the voltage waveform which will be appearing across the load is somewhat like this. We can see here in the DSO also, the waveform is represented as this clipped waveform, and we will see mathematically once we'll cover the rectifier portion. We will see how to basically analyze those waveforms and see the average output, how it has to be calculated. Now let's see some of the data sheets, or how does these thyristors looks like. As we have already seen, it can be in 3-terminal device as represented here by a make which is Vishay semiconductor, and it is available in the form of 1600 volts to 20 amperes, and we can see these 3 terminals as anode, cathode and gate. Other devices here we can see in the disk form, these are used for 1400 volts, and the name of the device is generally written over the device here. And other type of device here we can see the mesa type, which is represented where this nut kind of a thing is represented as anode, and where we can see now here the gate and cathode is in uh, red color small wires. So we will cover the application note and how to read the characteristics specifically for choosing a thyristor in next slides. So thank you for this session. We'll meet in the next session.